compatibility. I mean, okay, anyway, now we have to get down to, we found everything. It's just not working. So, I mean, even very experienced people might have to talk to Envy to see, you have to tell them specifically what hardware do you have. Maybe it's an old machine and
I
they
need a
don't
new
actually,
computer.
they don't support.
Yeah.
So I show you what happened when I do mine.
So we could put you in contact with Eric, and he can maybe see if he can fix that.
Yeah.
And if not,
My
then-
computer's old. It's had water damage and been dropped and bumped and everything, so it could just be that. I was trying to wait until I graduated to get a new one, but
Yeah, well, I guess computers do have their limits about how much you
Yeah.
can abuse them before they stop working, right?
it's not looking great.
So does anybody
Okay.
know if the guy who usually sits on the end is coming along?
Michael was here.
No, the other guy. He usually comes though.
Right.
I don't know.
Oh wait,
anyone
he
knows.
said he might be not coming to this one because he only had a Chromebook and he was using his Windows computer at home.
Oh.
So
Okay. Right, and I guess we're good. So, so yeah, what we're going to do. So, you know, we've spoken a bit, and we've spoken about this reflectance spectroscopy thing. And I'm not going to go through it again. We'll talk about it in a class. But you know, we're making measurements from square-ish areas on the Earth's surface from a distance of 700 kilometers. We're sampling the light or the spectral radiance that comes from the sun, hits the target, gets changed, bounces back up. We sample that and we look at these square areas which can be in variable size. That comes up, we split it into its different component frequencies. We take that light, it's intercepted by the detector, photons are converted into photoelectrons, and at the end of that thing we get a digital number. And I told you the digital number is related to the reflectivity properties or the amount of light or the number of photons even, or the photon flux being reflected by materials we want to chemically fingerprint. So today what we're going to do is just look at some real satellite data of Hawaii. So, you know, most of you are interested in planetary science like Mars and Mercury and Uranus and all that sort of stuff, but you know, the Earth is a planet as well, right? So I'm going to show you some data, and show you some data of Hawaii, because this is a part of the world where we live and we study, and maybe you'll be a bit more familiar with it. And it can be easy to explain some of these concepts looking at things that you know, rather than me pointing out minerals that you've never heard of. So, as I mentioned in class the other day, we're going to do this in a piece of software called Envy, which you've loaded up. I produced this lab. So this shows every, I am sure, and I'll go through it on here as well, every mouse click and option that you need to press on in order to make this lab happen. So it's okay to fire up Envy if you like, and I'll show you what success looks like. I would say, so we're going to go through this together. So even though you've got the handout, don't go rushing off ahead of everybody and get to step 20, because what invariably happens is I'm talking about stuff up here that explains what you're doing, and then at some point somebody says, oh, it's not working anymore. And I say, well, which step went wrong? And they say, well, I don't know. And it's like, well, you're at step 100 out of 200, and I don't know what you did wrong on step 78. So invariably people have to go back to the beginning. So please be patient, even if you're quick. That one,
Yeah. Easy.
so let's first see what I was going to talk about. Okay. So when you fire up Envy, you want success looks like, so you get that thing first or something similar. I think I'm using a slightly older version, but it's still good. And then eventually you'll get this workspace, right? So everybody should have a thing that looks like that. It looks different on a Mac and it's different in Unix, but it's something like this, right? So there is a version of Envy called Envy Classic, which is the old version of Envy, which was far better than this. It just gave you a menu with about 8 words in it, and from those words you got to everything else. But they decided that, I don't know, people like complicated desktops, I guess, so now they make you operate via this GUI type thing, which is a pain in the arse. But it's in the other class that I teach, we were teaching Envy Classic for the longest time because we basically hated this version, but this is the new version, this is the version that's not going away, so it's a disservice to you lot if we teach you the version that's more comfortable to us, right? So even though this is worse, if you do this kind of work and use Envy, you're just going to have to suck it up, because this is what Envy's going to look like from now on. So we're going to, you can see there's a bunch of stuff in here. Has anybody done any image processing before? Yeah, so this is what we have here is we have the file manager or the layer manager over here, and I'll go through it, and then other boxes are going to come up. But this is basically where you know what files you've got open, right? And then another box is going to come up, which are going to show you the spectral bands that you're using at any one time. So remember, we take the light, we split it up into different frequencies, wavelengths, or colors, and each one of those is going to be called a band, a spectral band, right? So if we say that we have a 3-band composite, that means that we're looking at light measured at 3 different wavelengths displayed in the 3 different display colors, right? And the number of bands is basically described as the spectral resolution. So the data I'm going to show you now, we're going to look at the EO1 Hyperion has 220 something bands. Landsat has 6 or 7 bands, right? But that's on kind of the left-hand side. In the middle, you're going to see images, and you're going to see graphs and plots and spectral signatures. The right-hand side is what they call the toolbox. So classification is image segmentation or clustering. People have done image processing type work. Filtering is filtering, low pass, high pass, edge, median, all that sort of stuff. I think there's some Fourier filtering in there. Image sharpening, mosaicing, so stitching images together. So there's a whole bunch of stuff in here, most of which I don't know how to use because I don't really use Envy that much. But Envy is a really powerful tool. So, like I said the other day, this is, if you go for a job at NASA JPL, this is what they're going to be using to do the work. Right? You become an expert in this by using it. Right? You don't just know it. It's that thing. You learn how to use it by using it. So what we're going to do first is, and everybody needs to be. So I'm going to say the only thing I'm going to assume is that when I say open the EO1 file, you know where it is, right? In the directory structure of your machine, right? So let me just show you how to do that first. It's written down here. So this is an EO1 Hyperion sensor image. So it was acquired, as I said there, on the 6th of February 2003. All of the data I'm going to show you are freely available, and I'll dump the website in the Laulima at some point. NASA and the other space agencies, they now basically make all of their data freely available, right? So you can just go and grab it and download it and analyze it. When I was doing my PhD, I was using data from the other sensor we're going to use, the Landsat Thematic Mapper, and I think we had to pay like $3,000 per image. Right. Now you're not limited to that. You can download as much data as you like and analyze it, which is really good. So if we go here, so we're going to open a file. So if we go to File, top left, and obviously there's a bunch of shortcuts here, right? So beneath it, you've got the toolbar. Hey, how you doing? Grab a seat so that you can see the screen. Oh, yeah. We'll just wait for you to get set up. So any questions while we're just waiting for a few minutes? No? Okay. So the reason we're using these 2 images is partly EO1 is a high spectral resolution sensor, so 242 wave channels between 0.4 and 2.5 microns. Landsat is a low spectral resolution sensor. It has like 6 wave channels between 0.4 and 2.5 microns. They both have exactly the same spatial resolution, so 30 meters. And EO1, when it was launched, it was a tech demo mission. It was basically trailing future technology to replicate Landsat in the future. So they were in the same orbit. So they were in the same orbital plane at the same altitude. And they were actually, they went over Hawaii within a minute of each other, right? Because they wanted to acquire data with Landsat and acquire data with EO1, and then just demonstrate that the EO1 data could be used to replicate Landsat products accurately. And on the Earth, fortunately for us, unfortunately for remote sensing people, we have an atmosphere which is really variable. So they wanted to minimize the time separation between the acquisition of the 2 data sets. So they had them flying in formation with just 1 minute of separation. Same altitude, as I'll show, there are significant differences between the data, but that's what EO1, it was a tech demo mission. You good?
Yeah.
Oh, wow, great. Okay, so I'll point some of these things out, but if you float over the tool, there's this ribbon at the top, you'll see that words come up. So that's file open.
If it's-
I'm going to show you, there are some shortcuts written in the menu, some control I's and control O's and stuff like that. But to open this file, we're going to do it the brute force way, and we're going to file, open, surprise, surprise, right? And then that's going to open up one of these dialog boxes. I presume it's similar on a Macintosh as it is on an IBM. So then just find the file. So here's the thing about Envy. You'll see in here, let's take a look at the one we're going to open, which was EO1 Big Island DN. So that's that one, right? Just there. So you'll notice here, I've got two files. I've got EO1 Big Island DN, which is a massive file, right? It's 1.3 gigabytes. And then I've got this other file here, EO1 Big Island _DN.hdr, right? So the HDR file is a header file. Do not delete or separate these files, because the header file is the set of instructions that Envy uses to know how to open the image file. So the big file, or the flat file that people call it, is where the data are stored. So that's the file in which all of the DNs in all of the bands are stored, right? But you need the header file because Envy doesn't know how to open that file. So I'll just show you what's in it. And this is just like you can open this as a text file. Right, so that is the header file. So if we look in it, there are a few really important pieces of information. So one is samples and one is lines. This is basically the number of pixels in X and Y. Right, so remember we have a two-dimensional radiance map, or DN map. And this tells Envy how wide it is, and this tells Envy how long it is. And it has 198 bands in it, or 198 spectral channels. So we have 198 different maps of DN, which are this wide and this long. There's a bunch of other stuff in here. An important one is this, data type 2. So data type 1 would be byte data, data type 2 would be integer data. Right, so 2 bytes. And what that tells you is the computer needs 2 bytes per pixel to store the DN. The final important piece of information, or really important piece of information, is this, which is the interleave. So BSQ stands for band sequential. So what that means is this is just a stream of numbers, right? So it's a stream of numbers. If you take, and if somebody has a calculator quickly, they can do this. If you multiply 1039 by 3411 by 198 by 2, you should get an answer which is rounding dependent, something like 1.3 gigs. Anybody done it?
Oh, it was like 2.7.
Was it?
What are the numbers again?
1039 times 3411 times 198 times 2, because it's 2 bytes per pixel.
1.4.
Right, 1.4, right, which is, and I showed you in the file manager, it's about 1.4 gigabytes, right? So I pointed out the other day, people love hyperspectral resolution, but that's a big file, right? And the thing that's driving up the size is 198 bands, right? But the flat file is just a stream of numbers, right? So before Envy can make an image, it needs to know, well, where do I cut it off? I need to know how many X, right? Otherwise, I'm just going to stream this out. So that's why it needs the samples. It gets to the end, and it's like this thing, you can't be underdetermined in any kind of math problem, right? So the file size 1.4, Envy knows that. It then needs to know those 4 numbers, sorry, those 5 pieces of information: samples, lines, number of bands, the data depth, whether it's byte or integer. And finally, the band sequential thing means we're telling Envy, okay, all of the DN in band 1 come first, and then all of the DN in band 2 come next, and then all of the DN in band 3 come next. So that's band sequential. The other 2 that you see are band interleaved by line, in which case Henry would say, okay, the way this is stored on the disk is I have the first row of values in band 1, then the first row in band 2, then the first row in band 3, then the first row in band 4, etc., etc. So that's band interleaved by line. You're just interleaving the bands by line. And then the next one is band interleaved by pixel, which is the first number is pixel 0, 0 in band 1, then 0, 0 in band 2, then 0, 0 in band 3, and etc., etc. Right. So if you don't have those 4 pieces of information, Envy has no idea how to open this file correctly. You'll see there's a bunch of other stuff in here. I put some map information in it because this is geotagged, so every single pixel has a geographic location, right? So we know where on earth it is. And there can be other information in here. For example, here wavelength unit nanometers, right? But a lot of the other information you can add later. But if you don't have those 5 pieces, then you just and you can't guess, right? There's no way you could guess that. So that's the reason, do not separate the header file from the data file, because otherwise you'll never be able to open it. Right. Usually the header is a separate file. There are some weird data sets where they actually roll the header into the first n bytes of a file, right? But again, the software has to know that. Okay, so we've got a header and we've got a data file, and we're going to open EO1 Big Island DM. Oh, that's the wrong one. So we just click on it, and you can click on the header or the file, right? And then just click open.
Yeah, that's what I'm thinking I will do, open reason.
Okay, so has everybody got something that looks like that? Nope.
Okay.
Eventually it will.
You can, but that really makes no
Well, this is file information.
Okay, so you might want to close it up and start again. Something
Yeah,
like
I
that.
think that's, well, I have the same thing, so.
You have the same problem?
Yeah, this okay, I will.
Oh, you do?
Well, you hit the
Oh.
mouse and moved
Okay.
into you zoomed into the
Do you have an image?
You know how it's just
No,
a
my
band?
thing
Yeah.
crashed.
You
You got
zoomed
it?
in
You mean
on
one
the
way or the
corner.
other?
You zoomed in on like a
You have an
corner
image?
somewhere.
Oh, okay.
But I was trying to zoom
You
out
have
and I
an
couldn't.
image? You have an image?
We're doing the Hawaii lab.
You have an image?
Wait.
Yeah, yeah.
No.
Zoom
Oh,
out,
you have a
yeah.
handout.
No, I'll try it again.
Okay, so
We have to decompress
Hers
it,
was
right?
on
Like,
there.
Envy doesn't
She
open
hit her
zip
mouse and
files.
it kind of moved.
Like, what's
I
that?
just can't find it.
Yeah, I'll just read.
Yeah, me
Nothing
too.
to zip around.
Oh, so hang on a minute, you've got the data.
Like, I don't
Okay,
have
so
to-
this is okay, okay. Hang on a sec. Macintosh people, hang on a sec, right. One person talks at a time, and that's always me. So Macintosh people, the data have loaded, it just hasn't loaded up the bloody image like it does on a PC. Okay, so I will find it for you, so there's your handout. So, did you close it or did you open it?
No, I opened it and
So hers is open just fine.
Well, it blinks a long time and then it opens. Every time I do a command, it blinks.
I think I'm gonna ban Macintosh computers.
And then eventually it opens.
You should get a PC.
No, but you are not using NV.
Yeah.
Anything else?
Apart from anything else, they're generally like half the price of a Macintosh.
Oh no, this is like
Really?
$1,000.
All the ones I've been
Right,
looking
so-
are
so
still
this is
like
good. Can you-
800 to 1,000.
What do we
Could you
want?
just work with her and see if you
I mean,
can generate that result? So don't load anything yet.
Okay.
Right, but, see, because she's using a Mac and it didn't work for her in the way it worked for you.
Weird. Okay. So you open the file, right?
But instead of buying an iPad.
Yeah, so you click on that
Yeah, I
file.
already have that.
Yeah.
I mean, honestly, our people, they buy, some of my people, I have to approve all the purchasing, they buy Macintosh computers from the bookstore. I see these purchase orders, like $6,000.
No, this is
Desktop.
$1,000.
For a desktop
Oh, the
computer.
desktop, sorry.
Oh,
That's
okay.
what I-
And
And
it's
this
like,
is an
oh yeah,
M2.
the monitor's $3,000. It's like, go to Best Buy, and get like a Sony
Why-
A TV.
HDR
Yeah.
OLED TV
Mine
for
do
half
that.
that price. It's incredible.
surprisingly
One
good
more
PC
time, one more
monitors at Costco.
Costco's
I
great,
paid
yeah.
$150 for that.
Yeah.
Big Island DM, yeah.
Yeah,
That's about
I
right.
try to open it and then none of the data loads.
But it's not, but nothing happens. So
Yeah.
the data manager, see what you've got over there is a thing called the data manager,
Yeah.
which is this. And hers is empty.
Yeah.
Unless we can get it in there. Let's see if it just like that. It's doing something. Okay, well,
Which
you
computer is
you may have to let's get going, right? You may have to just try and talk to Eric so you can get it going and do this in your own time.
Yeah,
Right, because yeah, fixing is not it. So let's go back and let's sit down and I'll show you how to load something.
if you like it.
Oh.
Mouse will help.
So that-
Yeah, it's insane to have to do command shift.
Oh, here we go. That's it. Okay, well, for whatever reason it's just not displaying.
Hers was on
It was
there.
displaying
It did
before.
display.
It did display once and then it goes.
Can you
Okay,
zoom
I
all the
know.
way out?
Yeah, that's what this,
That zooms
that's
all
what
the
that
way
does,
out.
that's sends it to the extent. Oh, no, isn't it? Zoom to full. Oh, there
Oh,
we go,
there.
there we
Yeah.
go, okay, okay.
What did you do?
You just
Zoom
zoomed out.
to full extent.
Oh,
Yeah.
okay.
Okay, but I think
I was
it's just
trying to tell
nothing
you,
is
you-
appening in your data
Your
manager,
cursor
which is
was
the
right
problem.
here, you
Oh, yeah.
hit it,
Oh,
so
I
it
see.
zoomed into the corner.
So if you wanna sit
That
with
was it,
somebody
yeah.
and just like work with them or something like that.
Is this what it should look like when you open it in text editor?
this
Yeah, it's a binary file that
basically
you're,
what-
Okay.
you're looking at an ASCII editor.
But it's
Okay.
happening,
Yeah.
that's why it's hard
Yeah.
to share.
Okay,
This way
so,
is better than if it's over there.
So this is what Envy loads. So there are a couple of things. If we look at this, what it's just loaded is a simulated true color composite, right? So everybody can do this. If you go to this thing here, this magnifying glass, zoom to full extent, and click on it, then it should go from that to that, right? Everybody got that? Yeah. Okay. So if we look at this image, this is a simulated true color image. So you remember I said our instruments measure reflected photons at different wavelengths, some of which are visible to our eyes, some of which are invisible to our eyes, right? When we're looking at it on a screen, obviously we rely on light that's visible to our eyes, right? So the display monitors emit red, green, and blue photons, and that's how we see what's on the screen. Okay. A simulated true color composite, there's only one way of making it. If your spacecraft makes measurements of the number of photons reflected from each pixel at visible red, green, and blue wavelengths, right? And you encode that in terms of visible red, green, and blue wavelengths, then you create a simulated true color composite. And what that means is, what you see on the image is kind of like the colors and the relative colors that you would see if you were sat on the spacecraft looking down at the ground. Right? It's called simulated true color because our eyes don't have cut on and cut off frequencies. You know, the cones on the back of our retina, they don't stop and start being sensitive to red, green, and blue light in the same way that a filter device would, right? So it doesn't look exactly like it would to our eyes, but it's pretty similar. So this is the Big Island. So do we agree that water tends to look blue? Right. When you fly over to the Big Island, does it look that blue? Right. The open ocean does not look, it's a dark blue, right? And the reason it's a dark blue is the photons strike the surface, we get some first surface reflectance, specular reflectance. Snell's law dictates we get some refraction across that inner refraction boundary. Photons start cascading down the water column. and some get reflected back, but basically because water is a transparent medium, the photons go down and down and down and down. If they don't hit anything, then they don't come back. Right? So water is a very, very dark target, very low signal to noise. What we're doing here, and we'll show in a couple of pages, we're just tuning the contrast up, right, to make it look brighter. The Big Island, in this part of the Big Island, is kind of green, right? So Hilo's just off to the top left there. You know, there's a lot of rainforest, right? It rains a lot on that, the windward side of the island. There's a little cloud there, which looks kind of white. Really clouds look white. And then you can see a little cloud shadow as well, just about here. Right. The image swath here is 7.5 kilometers, right? So the way the spacecraft works, the orbits are coming down in this direction, right? The width of the image is only 7.5 kilometers. What would the temporal resolution of that spacecraft be? Remember we did this calculation the other day? So it's in the same orbit, it's in a 700 kilometer sun-synchronous orbit, which means the period of the orbit is 90 minutes, 24 hours in a day. Divide that by that, you get 16-ish. 7.5 kilometers times 16 would give us a number that somebody could work out. Sorry, I don't do math in my head.
120.
120. And the circumference of the Earth with a radius of 67,000 kilometers is about 40,000. And then if we divide 40 by 120,
40 by 120 or
40,000 by 120.
333?
300, right. So this spacecraft goes over Hawaii once per year, right? So we would say the temporal resolution is awful, right? Remember we had that temporal resolution thing, which is how often do I see the same target on the surface of a planet, right? With this spacecraft, we see it once a year, right? Which is terrible. I mean, if you were interested in studying vegetation stress and health, you need more images than that, right? If you're studying drought, you need more images than that. That's okay, because as I said, this was a tech demo mission, so it was just designed to space qualify technology for use in future missions. Right. So if you go here and click on this thing, which is the data manager, right, if you don't have it up already, then this is an important window as well. So this is always worth keeping open in Envy. So as I said, over here, this tells you what files you've got open.
One of these.
This tells
Oh,
you
here.
the bands that you have available to you to manipulate using the toolbox on the right-hand side. So if you just look here, EO1, Big Island DN, and then if you look here, we've got tons and tons of bands, right? Going all the way down. There's a band number, which is just here, B82, B83, B84, etc., from 1 all the way down to actually 224. The number over here is the wavelength of that band in nanometers, right? So this is important information, right? Bands really doesn't tell us any information, right? Band 83 means nothing. But the fact that I know that band 83 corresponds to a wavelength of 792 nanometers or 0.97 microns, what that's telling me is if I look at that image there, band 83, that's a map of the amount of spectral radiance reflected from all of those pixels at 970 nanometers. Right. If you look here, file information, so this tells me a lot of stuff that was in the header file, right? So again, we've got lines, samples, and bands, band sequential. We've got, you know, the file size, as we agreed, is 1.4. There's some stuff here, projection, datum, pixel size. So we'll look at it in a minute. The pixel size of this data is 30 meters, right? So 30 by 30, which is 900 square meters. So that's the area of ground that the spacecraft sampled during the integration time to make a spectral radiance measurement. And then when it got to the spacecraft, it took that light and using a diffraction grating like we looked at the other day, it split it into all of these different bands. Right. What else we got in there? So projection and datum. So quite often, sometimes when you get satellite data, it has no geographic information associated with it. So you might recognize it, but you don't know this pixel has this location on the ground, this pixel has this location on the ground. Right? This is telling me that this file actually has geographic information associated with it, and the projection is UTM. Does anybody ever heard of that? UTM, Universal Transmemoricator. People know lat long, right? Lat long as a way of locating yourself on the surface of the Earth. It's not terribly precise, right? UTM is a system that is, if you like, localizes coordinates for a part of the Earth's surface, and instead of reporting it in decimal degrees or degrees, minutes, and seconds, it gives you a location in meters from a point of origin. So in that way, you can use UTM to locate yourself to a meter on the Earth's surface. I won't get into it, but there's a load of UTM zones. WGS84 is the datum. So WGS84 is very common in satellite remote sensing. It's basically the Earth is kind of a fat sphere, right? Bulges in the middle. It's also very lumpy, right? So around India, where you got the Himalayas, a big lump. The Pacific Ocean is like an anti-lump, an endowment, right? WGS84 is a shape which gives a good whole Earth approximation to the shape of the Earth, and it's centered on the Earth's center. So what we use that for is basically, it's like a parallax thing. So if I know the location of that, if I look at a mountain and I'm looking down on it, then and I know the distance of that point relative to that point on the side of a mountain, right? To correct that to horizontal distances, I have to do that, right? Because otherwise there's a cosine angle thing which is causing 2 points to look closer than they actually are, right? Using a datum is how you reference a point relative to a local datum. So a datum that you've all heard of is sea level, right? People often say that the height of Everest is 8,000 kilometers above sea level, right? WGS84 is like a above sea level thing. It's just a way of us relating relative heights on a lumpy Earth. Obviously, if you're looking at images of Mars, you're not going to see WGS84 and UTMs, but there is, as you might imagine, a Mars datum. Right? People still want to talk about geographic locations on Mars and the Moon and Mercury, and they have derived data equivalent to mean sea level of WGS84 for all of those planets, and geographic coordinate systems. Right? And then the wavelength range here, 426 to 2300 nanometers, 2400 nanometers. The other useful thing is this thing here. So this is basically how you vary the spectral channels that you're viewing in the window. Okay. So we're going to do that next. So this just Envy loaded up automatically, although it didn't do it for the Macintosh users. It loaded up this simulated true color composite, right, which is a good place to start. But we can display any of these other bands, right, in red, green, and blue. So the first thing we're going to do is, let's do this first. So what bands do we have in there again? Remind me. We have 29, 20, and 12 in red, green, and blue, right? So let's just flip the order of those bands. Let's put 12 in red and put 29 in blue. So the way we do that is, if you look here, you see this one's highlighted, right? That means whichever thing I click on here is going to go in the red channel. So if I just go up to, and I was going to put 12 in there, if I go up to band 12 and I go 12, you'll see 12 just appeared in there. And you'll see it also moved down, right? It automatically highlights the green box. Yep. So in that one, I'm going to leave that the same, and I'm just going to leave that as band 20. And then it goes down to the blue box. People still good with me? Right. And then we're going to flip red and blue. So I'm going to put band 29, right? And then I'm going to load this in a new view so that we can see these two things side by side. Right, so at the bottom of this, click this box here, load in new view. If you don't click that, it just overwrites the image that you've already got up, right? And then if you click load data,
Load data in new view.
right, and then you might have to do this thing again, right? So let's just move this off to the side. You'll see I've now got two views, right? The active view is the one that has a bold border around it, right? So in this one, I'm going to click on that, and then I'm going to go back here and maximize the extent using this magnifying glass, right? So it just fills. And then here, the hand allows me to just drag these things around. Okay, so has everybody got something that looks like that? And you'll see, if I click on, this is always a good one. If I click on that, it activates the left-hand window.
Okay.
And then if I click in the window, it activates the right-hand window, right?
Oops,
So 2 images,
I tell you,
right? So you can still
Okay,
see it's the
this
big
is
island, right?
sensitive.
Okay. What happened? What are the major differences between these 2 images?
The color.
Right, colours. I'm still looking at the same wavelengths of light, all right? I'm still looking at the same bands 12, 20, and 29. I've just changed the display order, right? And now the ocean looks red, and the vegetation looks cyan. The clouds still look white, but that's just a happy coincidence, right? So this is what you call a false colour composite on the right-hand side, because the colours are false, right? Anything which is not a simulated true colour composite is a false colour composite. And people use false colour composites to attract your eye to certain things that they want to enhance, and we'll create a couple of those later. If you imagine that you are interested in mapping vegetation, right? If you colour vegetation as red, then that's an instantly attractive colour to your eye, right? It's why exit signs are red. It's why danger signs are red, right? It instantly grabs your attention. So people use these false colour composites in this kind of image processing, because if you're making a map, if your science project and your science product is a map of vegetation, colour it red, because the person you give it to may not know anything about remote sensing, right? But if it's red and you give them a key that says it's red, then they know what you're trying to communicate. There's an interesting book that was written 30 years ago called How to Lie with Maps. Have people seen Magellan images of Venus? So Magellan mission was like the late 80s, early 90s. It was a radar mission, backscatter mission. Venus is covered in clouds, right? So you can't use this kind of remote sensing. Fire down energy, measure the backscatter. The images are inherently grey, right? Because you're just looking at backscatter strength at one wavelength. So when you just load up the image, it looks grey. The images that you see when you Google Magellan Venus, they're kind of red and orange. Which makes sense, right? Because the Venera landers that went to Venus, the Russian landers that went there back in the olden days, they took images from the surface of Venus, and it looks kind of yellow. We know the surface of Venus is really hot, right? So you colour it as red, and it gives the impression of it being hot and all that sort of stuff. They could easily have coloured those images blue, in which case you'd have looked at it and maybe thought that Venus was cold. So again, false colour is just to draw attention to things. But it's the same thing. So now let's have a look at just load any triplet and do it in the same way. And let's first activate the right hand window so that we keep the first one up, and then just pick anything. So I'm going to pick this. I'm going to show 2 micron radiance in red. I'm going to show 1.5 micron radiance in green.
Loud again.
And I'm going to show visible red radiance in blue. And I'm going to load it. I'm not going to make a new view. I'm just going to replace that one.
Don't do anything. Okay. Oh, change again.
And then all I'm going to do is zoom in, right? So when you're in an image window, if you just use the mouse roll, you can zoom in and out, right? Or if you don't have that, you've got to zoom in and out and pan up here in the ribbon, right?
Wait, whatever color, it doesn't
Are you changing it to any color?
Anything you
particular-
like.
oh,
Any
alright,
triplet
so
you
we
like.
just like
So click the red.
whatever it is.
Oh, now it's click
Oh,
the
this
green.
will, let's say, let's go further, different. Oh, go down is more fun. It's tons of color. Okay, and then let's just say, a little bit later.
So I've just produced another false color composite image, right? So the image on the right hand side is still false color, right? Because I'm not using red, green, and blue in red, green, and blue, right? I've chosen about 2,000 nanometer radiation in the visible red, about 1,500 nanometer radiation in the visible green, and then the visible red in the visible blue, right? So this is a false color image, and it looks different, right? So significant difference is the ocean is now jet black, right? It's no longer blue, it's now jet black. Another difference is, you see these white pixels, we'll talk about those later at the coast, right? They are now no longer white, they are vivid blue, right? A lot of the fields are still kind of green, but again, that's just a happy coincidence, right? But we can still interpret this, right? Because you remember those three intersecting spheres of red, green, and blue, right? So this is how we interpret one of these images, right? So remember this, because it's really this simple, it's embarrassingly simple. So I am looking at two wavelengths of light which are invisible to my eyes, and I'm encoding visible red reflectance in visible blue light, right? So on one level, the colors make no sense, right? But I can still interpret this in terms of signal strength, right? And if you remember, the way you do this is pretty easy. I find a pixel which is black, first of all, right? How do I make black?
All colors.
All colors being,
Absorbed.
right, or an absence of reflectance, right? So if I see a black pixel in an image, that's telling me I was getting no reflectance from those pixels, which you're correct means I'm getting really high absorption from those pixels, right? In red, green, and blue, right? Because that's how I make black. I have an absence of red, green, and blue light. The next question is, well, what spectral bands do I have loaded in red, green, and blue, right? And in my case, I had 2200 nanometer light in red, 1500 nanometer light in green, and then like 700 nanometer light in red. Right? So what it's telling me is these surfaces are reflecting no photons with a wavelength of 2200 nanometers. These surfaces are reflecting no photons with a wavelength of 1500 nanometers, and these surfaces are reflecting no photons with a wavelength of 700 nanometers, right? Or they're absorbing light really, really efficiently at those wavelengths, right? And we'll talk about this later, but that's water. Water's a very good absorber. It's a spectacularly good absorber of infrared light, right? And in fact, water doesn't transmit much light, and the peak transmission is in the visible blue, right? So water is very good at absorbing visible red light as well, which is why the water looks black. You have a question?
Oh,
Oh, just a stretch.
yeah.
Again, we'll take another one here, right? In this image on the left, I have let's pick this one. I have a green pixel here, right? So in the image on the right, it's green. Why? And let's take it through these steps. Why is it green in this image?
It's reflecting green.
In
that wavelength.
right. So this is one way you can do it is I have high signal in the green channel, and I have low signal in the red and the blue channels.
But that doesn't mean it's reflecting green light.
Right, so that's the next question, right? Which wavelengths do I have loaded in red, green, and blue? Now in this case, this is a map of visible red reflectance in red, visible green reflectance in green, and visible blue reflectance in blue. So in this case, that does mean that this patch of ground, this 30-meter patch of ground, is reflecting lots of visible green photons, right? Because this is a true color composite. And it means that whatever's in that pixel is absorbing a lot of visible red photons and blue photons, which is how I make green. If we go to the same pixels, we have these three stripes. If we go to the same pixel in the image on the right, I can't find it, it's in here. But it's still kind of green, right? These pixels are still green. I've got green here and I can find a green one over here. So in terms of the first question, it's still the same answer. Why is it green?
Because it's reflecting.
Because I have strong signal
In the green channel.
in the green channel and
But a
less strong
certain-
signal in the, right? And less or more is based on that color wheel, right? So if it's yellow, that means I've got really strong signal in red and green channel, but not much in blue, right? But the next question is, which wavelengths do I have loaded in the red, green, and blue channel? And in this case, I have 2200 in red, 1500 in green, 700 in blue, right? So in this case, a green pixel is telling me that that patch of ground is reflecting lots of light at 1500 nanometers, but less at 2200 nanometers and less at 700 nanometers, right? So when you're interpreting these images and you, remote sensing, this is how you do it, right? We can design sensors that measure thousands of wave channels in wavelengths that are invisible to our eyes, but we have to encode it in visible light for us to actually see it. So what I've just described to you is how if somebody gives you a satellite image of the surface of the moon and it looks like weirdly colorful, right? As long as they told you that it's a red, green, blue triplet and they told you which wavelengths are loaded in red, green, and blue, then you can unravel that to say, well, if that pixel's magenta or pink, what that's telling me is whatever is in that pixel, and I don't know it yet, is really, really good at reflecting light in whatever I've got loaded in the red, the blue channel, but not the green channel. And then as long as they told you which bands are in the red, green, and blue, you can basically build a 3-band spectral signature, right? If you don't tell people the wavelengths, then the colors are meaningless, right? They're just colors. So one thing we'll quickly do as well, I haven't done this yet, but just select either of these and zoom in, right? So those are the pixels. Right, so if you zoom in and zoom in and zoom in, you start to see the pixels in the data set.
Oh, you mean this one?
Yeah.
And then that's.
So just go right in and you'll start to see the actual pixels in the data.
Right.
No, I'll just zoom all the way in, not on the right, just anywhere.
Yeah.
Okay.
But let it, and then it might have to. Okay, I don't know what yours is doing. Maybe it'll take a while to refresh. But everybody else has got something that looks like that, where you can actually see the pixels, right? So these are the 30 meter by 30 meter patches of ground that EO1 divided the Earth's surface into to sample the radiance,
Give me some more, no.
right? Everybody got this? So this is the pixel size of the data. Each one of those patches of ground is 30 meters on a side, right? So we call that the spatial resolution of the data. And you'll see this isn't great data. If you were if you were a surveyor and you wanted to map roads, this isn't the best data you'd use, right? We can work out something like farmers' fields, but if we wanted to count the area of farmers' fields, this data isn't great, right? Because it's alias.
It's changing something, yeah.
Because that kind of information is sub-resolution. The way you would work this out, remember that toolbox equation I showed you in the first week, right? I showed you a picture which had the diameter of the optic, the size of the detector in microns, the focal length of the telescope in meters, right? And the height of the spacecraft above the surface, okay? If you plug all those in, I'm telling you that's 30 meters, and I'm telling you that this spacecraft was about 700 kilometers above the Earth's surface when it made that measurement. If I also told you that the pixel size was about 12 microns on a side, you could work out the focal length of the telescope,
Yeah.
right? But that's where that comes from. So these are 30 meter data, and I'll just go back out again. So what were we going to do? So the next thing we're going to do is just explore the images. So let's just start on this one on the right hand side. So there's a couple of ways. Control I, or you can click this thing here, which is cursor location value. Right, so this thing that looks like a Google Maps, whatever it is, icon, or you can hit Control I, and that brings up this other box, right? Again, in Envy, you've just got to be careful. If you have two images visible, you've got to click on the one you want to operate on, and that will give you this big black boundary.
Yeah, got it.
So everybody should have seen this box appear, cursor location value box, and then a crosshair, right? And this is this is not rocket science. What we've got here is it tells you, if you click on any pixel, so let's click on that one, what that's telling me is for that 30-meter pixel, this is its geographic location on the Earth's surface in UTM coordinates, right? To the top, it also gives me the same location in this case, degrees, minutes, and seconds. So these are more familiar lat-long numbers, right? But that's the geographic location for that point on the Earth's surface. And obviously, I don't know it I don't know it any better to 30 meters, right? Because that's the resolution of the data. It also gives me a couple of other numbers. This one here is the physical location of the pixel in pixels. So NV starts counting pixel location at 0, 0 in the top left. So in an image like this, the top left pixel is 0, 0. Right? So the pixel I just clicked on is 3,499 pixels by 2,100 pixels. And I don't know why it decimalizes it, because a pixel is our limit of quantization. Right? The numbers beneath it, these are the DN numbers. Right? You see these numbers here, the one I clicked on, I've got a number of 1136, 1468, and 1940. So I'm working on this simulate true color composite image, which I know the red channel, or the first channel, is visible red photons, right, or band 29. This number, the blue channel, is visible green photons, which is band 20. And then this number is visible blue, which is band 12. Right? These are the DNs in each of those bands. Right? So remember I said we are going to get a DN, and as long as we don't break that chain, we should be able to back calculate back to radiance and reflectance and all the good scientific stuff that we want to use. Right? But this is the DN. So if you remember, what was I said that if you have a spacecraft which has an 8-bit measurement range, what's the number of discrete gray levels that I can distinguish if it's 8-bit? Right, 0 to 255, which is 256 different gray levels, right, for an 8-bit system. Is EO1 Hyperion an 8-bit system? Can't be, right? Because I've got a DN of more than 255, right? So EO1 quantizes the data into a much greater range of gray levels than does an 8-bit system. So you would say EO1 has higher radiometric resolution, right? I can distinguish more subtle variations in intensity, brightness, but think about it this way. More subtle variations in how many photons did that patch of ground reflect to each of the wavelengths that I'm measuring. Right, that's really what we're talking about. So we have a higher dynamic range for the measurement itself. Sorry, I can't remember this. Okay, so those are the DN, and you'll see if I just click on this one. So let's click on something bright like this, and you see the DNs are kind of high, 1200, 1600, 2000. If I click here, they went down, right? 400, 900, 1800. Okay. So here, let's take the first channel. So over this ocean, the visible red DN is 439. Over this lava flow, the visible red DN goes up to 1300. So it kind of triples, which is telling me, to a certain extent, you know, this is not precise, but these lava flows reflect 3 times as much visible red photons as does the ocean, right? And that's not quite true, because the different wavelengths, and if you look here, the calibration, I included this, which is the calibration for the Landsat data. The slopes of those lines for the different bands are different. So the ratio between DN and radiance unit is not 1-to-1 for every channel, but certainly lava reflects more visible red photons than does water. So what we might want to do is see all of this, right? So we're just looking at 3 bands, right? And there's only 3 bands we can load in a display system. But I told you, EO1 is a very high spectral resolution device, and it measures a complete spectrum, right? We have a couple of hundred bands, a couple of hundred measurements. So it's very easy in Envy to just produce a spectrum in a little chart that shows you the spectrum for each point. So if you go to, and again there's a shortcut, we're on point number 5, you can either click this thing here, which looks like a spectrum, or you can hit the shortcut, which is Alt Z or something like that. Right? So if I click that, I get that. And again, I've selected this image on the left, so it's referring to the image on the left. And if I click around in this image, you'll see that the spectrum changes. Right? So I said that reflectance remote sensing was, squiggle hell. So this is just what we're looking at here, right? This is a spectral signature of whatever is in each of these pixels. So that's the spectral signature of the ground in that pixel. And that's the spectral signature of the ground in that pixel. And you can see it auto scales the y-axis. Question?
Is that the same kind of graph we were looking at last week? Like where it shows you which colors it absorbs and...
Not quite, we're going to get onto that. This is DN versus wavelength. So you weren't here actually the other day, but you remember when we first started looking with the spectrometer and we had counts against wavelength? That's what we're looking at here, just counts, just DN versus wavelength. So it's still a spectrum, but it isn't a reflectance spectrum because we haven't converted it to a reflectance spectrum yet. But again, this is, instead of 3 bands, this is showing me the complete spectral information. Yep.
How do you open that window again?
Oh, so you go to this thing here. It's in the handout, but this icon here just opens it up.
Oh,
Spectral profile. Yeah. Did you finally get yours working?
yeah.
Great.
Oh, what happened? This one? Spectral profile.
Thank you. Yes, that
And
was
this one
spectral
you do the
profile.
Yeah.
okay, so look at all of that and then you will do better. Okay.
So if we go down here, just go down to the ocean and just have a look. So this is vegetation here. So that's the spectral signature of vegetation in DN space, right? If we click here, that's the spectral signature of water. So very different, right? Again, these are just in DN space. So these aren't real units on the left-hand side. If we click here, we get something a little bit different than either of those signatures, right? But same thing. This is just a chart of, in each wavelength along the bottom, for that pixel, the DN, if it's high, that means lots of photons at that wavelength were reflected from that patch of the Earth's surface. If it's low, the inverse of that, right? So this is kind of a useful window. One thing you can do here, so don't do it now, but if you wanted to save that spectrum, you can just go export, and you can dump it out as an ASCII file. You both doing okay?
Yeah, maybe.
Our spectrum isn't showing up, it's just like a blank.
This is where he
And then
is.
also when we pull up.
Right. It's this patch, but
Yeah.
it's here and that, but it doesn't.
Are you trying to get the graph that matches his?
No, I'm trying to get the pixelated, but we never was able to do that, remember?
Try it now. It looks like yours is just.
Yeah, it just
Fuzzy.
doesn't, just doesn't do that. But this is the right place. You see,
Yeah.
this patch is
Yeah,
that
that's
patch and
the
that's, well, maybe it's a little bit better, but it's not completely like this.
It's just fuzzy.
So I do know
But it was like a laptop, maybe they don't have as much pixels. But
honestly, I have
in
no idea what it is.
general, you.
So
You're
this
in
one
the
just
right
has to
Yeah,
follow,
yeah.
right?
And. you
Other
can
people have
also-
got it. Okay, you ready?
Yeah.
So if you're interrogating Envy and you wanted to get one of these spectral signatures out because you wanted to feed it into an algorithm, remember what I said at some point, we want to go into one of these images and of an area in the solar system we don't know, and we want to say, well, I want to know the spectral signature of what is here on the surface of the planet. And then you want to take that spectral signature and you want to match it against the library, using that run length encoding thing that I described. If you wanted to do, you wouldn't do it like this, right? You'd write some kind of IDL script. But you can dump that out you can dump everything you see in here out as an ASCII file, or you can dump it out as an image file or a PostScript file or anything like that. Right. And we're not going to do it, but that's how you can get rid of stuff like that. Okay. What are we going to talk about next? Spectral profile. Okay, so now what we're going to do is we're going to open up another image of the same point on the Earth's surface acquired from a completely different spacecraft. Right. So the first thing we're going to do is close the image on the right. So here's a problem with the new Envy is your workspace gets really cluttered really quickly if you just keep opening images. So I think, so the way you can do that, there's a couple of ways. I'm going to close this for now. I'm going to keep this open because it's useful.
I close a window, but it closed everything, but it's okay.
And then here, view, this is the view that I have this loaded in. So I'm going to go remove view, and that just gets rid of the view. Right, so just right click on here, or you can do it in here. No, you can't. You have to go over here in the file manager and just right click on the view you want to get rid of. And then I'll make that to the full extent as well.
Yeah.
Okay. So now we're going to open a Landsat file of the same point on the Earth's surface, right? So point number 6, if you go File, Open, and then we go down to, I can't remember what I called it, ETM, Big Island, DN, BSQ. And again, you just click on it and go Open.
Which one again? No, it's okay. Which file?
It's in the handout. It's ETM _ Big Island _ DN .BSQ.
BSQ is down here.
So is your computer completely
Yeah, here. ETM, Big
Oh, trying to get it going.
BSQ,
Okay.
right? Yeah, that's it. Okay.
Yeah, so I honestly, I'd love to be able to tell you why some computers work and some don't, but
Yeah, so
I
it's not
genuinely can't.
only Macintosh.
You know, it's fucking weird.
Different computer works on different things.
Yeah. Okay, so this is an image at the same point on the Earth's surface, acquired by a sensor called the Landsat 7 Enhanced Thematic Mapper Plus, right? So as I said before, we'll look into this. Landsat is an operational mission that's been going since the early 70s.
Oh, you mean? Ooh, don't do that.
Right. You ready? You ready for some
India.
soul-crushingly important information?
Yes.
Yeah.
Right. So the first Landsat sensor was launched in 1972, right, which was the year before I was born. And it's basically NASA's, or the USGS's, environmental monitoring spacecraft. Right. So Landsat has the same spatial resolution as EO1 Hyperion, so 30 meters by 30 meters, right? The image swath for Landsat is 185 kilometers on side. So remember I said EO1, and you can see it there, the EO1 strip is 7.5 kilometers. The Landsat image is 185 kilometers. So we're not going to do it, but we worked this out the other day. We worked out that the temporal resolution of EO1 was 330 days. The temporal resolution of Landsat is 16 days, right? Because the swath is 185 kilometers. So again, if you multiply 16 by 185 and divide that by the circumference of the Earth at the equator, you get about 16. Landsat was designed to monitor the Earth, so it has a temporal resolution of 16 days because if you care about vegetation dying and growing, you need an image once in a while, right? You need an image in the spring and you need an image in the winter, right? Because that's when stuff greens up and browns down. When they were designing it, and this was a mission design thing, right? So this is the science traceability matrix. The engineers just didn't say, well, we're going to put it at 700 kilometers in a 98 degree inclination orbit, and we're going to have a swath of 185 kilometers, you know, suck it, scientists. They worked out, well, the scientists on the left-hand side of the science traceability matrix said, we want to monitor vegetation health around the world, the green up and the brown down in the forests, for example. So to do that, we need at least an image in the spring and at least an image in the autumn, and we need a couple more than that, right? So on the basis of that, you can work out in a year how many observations you need to get that done. Somebody then pointed out that on the Earth, you can pretty much guarantee that if you try and look at a point on the Earth's surface, it will be cloudy 2 days out of 3. right? And with these reflectance spectrometers, as you can see here, if there's a cloud in the way, we measure the spectral properties of the cloud, not the ground beneath it, right? And vegetation types don't care about clouds, they care about what's on the surface. So they said, well, you know, we need this many images, 2 out of 3 are going to be useless because they're going to be cloud contaminated. So that's how they came to this swath width. You know, the scientists and the engineers got together, and to meet the science requirement, they designed something which gave a 16-day repeat. Right. 185 kilometers, 7.5 kilometers. Do you remember when I mentioned whisk broom and push broom scanning? Okay. So the Enhanced Thematic Mapper Plus is a whisk broom scanner. Right. So back in the day, the first Landsat Thematic Mapper, so again, naming instruments. When you're writing a proposal to NASA, don't pick a name that somebody's already used. Increasingly, people like kind of acronyms which sound cool. So you've got to, when you do the capstone class next semester, you're going to have to choose a name for your mission or your instrument, right? So a huge amount of time is spent in pubs and bars around the Jet Propulsion Lab trying to work out what you're going to call your instrument, right? So the first instrument was launched in '84, which was the Thematic Mapper, right? Landsat Thematic Mapper. In 1993 on Landsat 6, that was on Landsat 4, they had Landsat 5. Landsat 6 was launched in '93. That quickly ended up at the bottom of the ocean. It was a failed launch. That had a thing called the Enhanced Thematic Mapper. It was like the Thematic Mapper, but better. This was launched on Landsat 7. It's the Enhanced Thematic Mapper Plus. So it's like Landsat, but better, and then better again. When they first started making these things, the focal plane array, as I mentioned, is really important, right? And it's hard to make a scientific measurement. You want very good detectors, right? You can't have a bad detector and a good detector and a bad detector and a good detector. They all have to be good, right? And you know, back in the day, it was hard to make detectors, large focal plane arrays, which were good. All of the pixels were good, like uniformly good. You could make 1 or 2 or 6 or 16, but you couldn't make 1,000 or 1,000,000 that all performed well, right? And it's a bit like your phones, right? They have slowly gotten better at making good focal plane arrays, which give you whatever the megapixel count of your camera is. Right? Because they could only have a small bank of detectors which were really good, they had to do this push broom scanning, this whisk broom scanning technique, right? Because if you took those 16 detectors and you projected them down onto the ground with the spatial resolution that they needed, which was 30 meters, again, that was in the science traceability matrix, then that 16 would give you 30 by 16, right? Which is, how much is that? Like a kilometer, right? So that's not 185 kilometers, right? To get the temporal resolution they needed, you have to take that bank of that small number of detectors and scan them all the way over to that side and all the way back to that side to give you the field of view of 185 kilometers. Right? So to achieve that, as I mentioned, you have a rocking mirror which oscillates really quickly. The mirror on Landsat's about that big, and it fluctuates furiously. It doesn't do this, right, because there's a big lever arm here because you're so far away from the world. But the mirror vibrates side to side, and it diverts light from those pixels onto the detectors, and then those pixels onto the detectors, and so on and so forth. And then by the time it has to go from one side of the image to the other. So 185 kilometers is about 3,000 30-meter pixels, right? It has to sample light from each of those 3,000 30-meter pixels in the time it takes the spacecraft to move forward 30 meters, right? Now, engineers will know what's the velocity of a spacecraft. It's about 7,000 kilometers per second in this kind of orbit. So what I just said, Landsat has to sample the light from 3,000 pixels in the time it takes a spacecraft traveling at 7 kilometers a second to move forward 30 meters. So that's not much time.
Okay, so
right?
good.
I mean, you can work it out pretty easily. We agree that is a trivially small amount of time, right? If it doesn't achieve that, then the images are blurred in this direction, right? So that ties back to this parameter, the integration time, right? Remember, as we showed the other day and I spoke about it, we said we can tune the integration time. If we need more photons, we can turn the integration time up, right? there's only so high you can turn it up, right? Because the amount of time it takes you to go from one line to the next line and complete that is the limit for the integration time, right? You can't program it for more than that, because then you'll be sampling not light from this line, but light from the next line and the next line and the next line. Okay. People see this? Yeah. So I'm just trying to point out some things which influence design. So you're all kind of engineers or astrophysicists. That is my, we'll just ignore it. That's one of my NASA program managers. You're all engineers and physicists, right? So you might be on the right-hand side of the science traceability matrix, or the instrument side, but the scientists are on the left-hand side, right? And they are going to give you these science justifications for why you have to include a rocking mirror in your design, right? And they have to justify that they need 185 kilometers every 16 days, because that rocking mirror is a pain in the arse, right? As I said, NASA's terrified of moving parts, and on Landsat 7, one part of the mechanism for the mirror failed on orbit, right? Which meant the mission kind of couldn't complete its work, because it could no longer do this scanning. EO1 uses this push broom imaging technique. So by the time they launched EO1 in 1999, they were getting pretty good at making larger focal plane arrays. So in that case, they didn't have to use the scanning mirror, they just used the push broom technique. So they just projected all those detectors onto the ground and then just swept them forward. Right. And that's part of the technology testing. They wanted to show that they could retire the scanning mirror. We go on to 1:30, right? Do you want to have a little break? Like 15-minute break, and then we'll come back and just carry on. Okay. So we'll come back at 5 to 12.
Do you help me
But I
troubleshoot
can't
this?
get it
It's
to
not
fit
loading the
to
image.
exact, well, it is almost, it's just the resolution is not the same, so do I have to go,
But when I'm
do,
opening
does it look
I don't know if I'm
exactly
opening
like
the
that?
file wrong, or something
More or
else
less,
wrong.
maybe I have to
You
move
zoomed
it.
It's just not loading the image.
I thought yeah, that's what I was trying to do, is to see whether I can zoom it out a little bit.
And I think it could be
No.
the ND
And
file.
then you can zoom into that spot.
Well, it's here.
Yeah.
So it's, no, not yet, I have to,
You can.
Okay, you get it up. I'm just gonna have to give this guy a quick call.
no.
And
Not yet. So the-
then
okay,
drag.
so drag it down. Yeah, that's close. Well, I think it's still a little bit too much. No, the other way. Maybe this is,
And then drag it back.
okay, so still have to go down a little bit. Clumsy. Yeah, that's pretty close, I guess. And I think just to do this.
So I'll do the NCE, and if there are any issues, I'll get in touch. I'll do that as soon as I finish. Okay.
You should still talk to Eric, see if he has any issue. Because you certainly don't want to hide your computer just.
Well, it's not just for that, there's a lot of
Also,
things.
it's,
It's been giving me trouble for like a year.
Okay,
I've just been
because,
putting it off.
because it's faster to begin with.
Yeah, I
This,
guess that was,
this is a really nice computer.
what year is this one?
This is maybe last year, M2, this is from M2,
Okay.
so that the thing came
I
out.
think I'll try to buy the cheapest one of them too.
Yeah, okay, the problem is then it means there's less memory and there's less this.
That's okay. I don't
But
need
the
that much.
memory, if you, but you're not gonna do
I know.
huge data.
The problem is that, like,
So where we
the
are
data
now,
is just not going to the graph. Like, it doesn't even show, like, except in the name itself, it doesn't even show there's any data being converted from that, like, part of NV to the next part of NV. So I think it might be something with either the files or the NV, like something got corrupted in that
talking
path,
about the
it's just
clock
not
now.
transferring over data.
Control.
Thanks a lot. Bye.
But I mean, I'm having issues too with it, where every time I load it in, it makes me choose my RGB values and.
Okay, so that's you just open the data manager, right, and you have to.
Yeah, I just don't know I'm on, like, the later in the packet.
Well, we'll see, right?
Yeah.
As it comes up. I'm buying a computer that I'm being told now is going to cost $500,000. And the first quote I got was $150,000, so I need to follow up with where that came from. Oh, did you get it going?
Yeah, so when I try to open the file,
Yeah.
I'm gonna get this.
Okay, so you go to
this
the
one.
DN, right? Yeah. Okay. So do you, hang on a sec, so click on this thing, the extend, that thing there. That's what worked for the Mac people, yeah, click on that. Was that a click? Or was it a double click?
Right there.
Okay, well, again, sorry about that, I don't know what to tell you. Weirdly, we now have it kind of working on Macs and PCs, but not on Chromebooks, I guess. Okay, so again, here's a thing, you could sit down with Eric, so people who haven't got it fired up on their computers, we'll arrange a time for you to sit down with Eric, right? And then, I think you'll agree this gives you every step you need to complete this lab, right? So, this will be you sacrificing a couple of hours of your spare time to go through it if you care that much. Sit down with a couple of beers and go through it. So everybody's back, right? So we'll just get on. Does anybody remember where we were? We opened up ETM Big Island, right? And we got this kind of thing, right? And I was discussing the thing, these differences in design, right? So the ETM plus image, the scientists wanted 16 days, which meant a big swath. And at the time, the only way the engineers could do it was have a scanning mirror because they weren't very good at fabricating large focal plane arrays, right? Scanning mirror is a pain, it's mass, it's complexity, it's a single point failure, right? If the mirror stops scanning, you're done. Right? So, as NASA moves forward, they want to space qualify better replacement technologies which will allow them to do the job with less risk and also less cost, right? So that was, okay, we're good at making these large focal plane arrays now, so let's dump the scanning mirror and let's just use this push broom imaging technique to acquire the data. You'll notice it's 7.5 kilometers, not 185 kilometers. They're now getting pretty good. So there's a mission called SBG, which they're going to think of a new name for. That's Surface Biology and Geology, which is crap. But they'll probably have like school kids have a competition to name it or something like that. That is going to provide 185 kilometer swath data like Hyperion. I remember another thing that I said, a challenge is if you make that 7.5 kilometer swath 185 kilometer swath, all of a sudden the gigantic amount of data you have to store on the spacecraft and downlink to the ground, right? Because the pixel size is the same and maybe the data depth is the same, but you've got 250 bands instead of 7, right? So you just massively increase the storage you need on the spacecraft, the throughput you need on the spacecraft, and the amount of time you have to pay for ground stations to receive the data. Right? And that's a big deal. I mean, you know, you'll find out next semester or something, the transmission of data to the ground uses radio waves, right? So you modulate the characteristics of a radio wave. So people have heard of like FM and AM, right? This is no news, I'm sure, to most of you. FM is frequency modulation, right? So if I tell you that, in terms of frequency, if I tell you that a 0 is and a 1 is right, so I've just modulated the pitch or the frequency. If I tell you that code, 0, 1, then we can communicate. I could communicate to you the entire works of Shakespeare in R's and R's, right? Frequency modulation, amplitude modulation is varying the intensity, so that would be R and R, where I'm just varying the power, right? On these spacecraft, we vary the phase of the wave, of the carrier wave, right? So they will use waves like X band or Ka band, and you vary the phase of the wave, and you can't vary phase without frequency, but they're varying phase. And in that way, they encode 0s and 1s, right? Our binary signal, that's how we transmit it to the ground. Now, if you're S-band, that's a longer wavelength than X-band, right? So the spacecraft is at 700 kilometers, and the speed of light is the speed of light. So if I have a longer wavelength, and the spacecraft comes over the ground receiving station, and it might, in a pass, it might see the station, right? You've got a dish on the spacecraft or an antenna, and you've got an antenna on the ground with these big dish type things. And the spacecraft traveling at 7 kilometers a second might only see that ground station for 13 minutes before it falls off the other side of the horizon, right? So if I've got 13 minutes to transfer data to the ground, can I transmit more or less 0s and 1s with a long wavelength carrier or a short wavelength carrier? So a long wavelength would be big waves, so I have a 0 and I have a 1, and I have a 0 and I have a 1, but it's moving at the speed of light, right? So yeah, the higher frequency carrier wave allows me to communicate more 0s or 1s in the same period of time,
Okay.
right? Because the speed of light won't change. So instead of using S-band, I might use X-band, right? Because that's a higher frequency. I have more wave trains and I can communicate more 0s and 1s, right? I could also use Ka band, which is even higher frequency, right? There are some problems. To generate an X-band carrier wave requires more power. So an X-band radio on a spacecraft uses more power than an S-band radio, right? So again, this is a design problem for you engineers, right? The scientist says, I want to have a hyperspectral imager, and I want 30 meter pixels, and I want this huge swath, and that's going to generate all this data on board. And it's okay because I've got a really big thumb drive that I can use to store it all. And then the engineer says, well, how am I going to get all this data to the ground, right? And they say, oh, just transmit it. And then you remind them of some physics like I just did. And you say, well, we're going to have to use an X-band transmitter, and you would work this out, right? They call this a link budget. You would work out how many 0s and 1s you can get down in a day to 5, 6, 7, 8, or 15 ground stations around the world. And you would say, well, I can't do it. Right? And the answer might be double the number of ground stations you use. And then you would come back and say, well, that just cost me twice as much money. So who's going to pay for that? They might say, go to a shorter wavelength or a higher frequency, and you get more data down in the same amount of time. The problem with that is, if you go to increasingly short wavelengths, the atmosphere starts to attenuate the signal. Right? So then you might be transmitting data down, but it'll be really noisy. So, again, just trying to point out the left-hand side of the science traceability matrix, the right-hand side, decisions made on the left-hand side easily translate into cost, complexity, dollars, risk, and you can't ask for something that isn't justified. At the same time, if the scientists justify it, and that's the only way that you can make the measurement that NASA wants, then the mission manager, that person might have to go back to NASA and say, look, I need more money. As I just did. Right, so data manager, blah, 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 blah. So it's already loaded it. You will notice. Okay, so let's just look at the image on the top. So this Envy doesn't necessarily behave in predictable ways, but let's look at the image on the top. So you'll notice, so I've had the same things loaded here. So if I click on this, it expands this, right? So in the file manager, if I click on that, then what this is telling me is I've got two images, one is on top of the other at the moment. Has everybody got the Landsat image on top? Right? For everybody's the Landsat image the foremost image. We'll show you this in a minute. You can move one back and one forward, right? But we'll keep this
So I
up.
already have that.
And has everybody got this kind of thing going on in the file manager? Yeah. So for the data set we open first, we have band 29,
This one.
20,
Yeah.
and 12 loaded in red, green, and blue,
Where is it?
right? And the wavelengths are 640 nanometers, 548 nanometers, and 467 nanometers, which we agreed were visible red, green, and blue photons, right?
There must be one of these.
Okay.
How do you make one in front and one in
Have
behind?
you got the?
Well,
you got
we
it flipped?
got
They were
Yeah.
open flipped.
So it doesn't matter at the moment.
Okay.
Look at this thing in the file manager. Right. So originally we had 640 nanometer light in red, 548 nanometer light in green, 467 in blue, and we agreed this was a simulated true color composite. Right. The Landsat image is band 321, so the band numbers are different, right? But we have 0.66 microns, which is 660 nanometers in red, 0.56 microns, which is 560 nanometers in green, and 0.47 microns, which is 470 nanometers in blue, which is basically the same, right?
Yes.
Plus or minus a few nanometers. So the Landsat image you're looking at is also a simulated true color composite of the Big Island, just acquired from a different spacecraft. As I said, the pixel size, the spatial resolution is 30 meters, it's the same. But Landsat only has 6 spectral bands. EO1 has like 240 of them. But here we're looking at basically the same thing. In each image we're looking at the number of visible red photons reflected from each pixel, the number of visible green photons reflected from each patch of ground, and the number of blue photons reflected. So as before, the ocean looks blue, right? The clouds look white, the lava flows look kind of brown, and the vegetation looks kind of green, although this is a crappy image, right? This is a great image, the one you had originally, because it had high contrast. And you could see that's not just green, that area of ground is pale green, and that's dark green, and that's bright green, and that's lime green, and that's green like your sweater, and all that kind of good stuff. What we'd say is this image has poor contrast, right? Because everything's kind of turned down and looks subdued. So what we're going to do next, I believe. Oh, here we go. Here's ADO. So number 8, we have 2 satellite images acquired by different sensors. In Layer Manager, right-click on the ETM file, go to Order, and select Send to the back. So you've already got that. So if we go here, Layer Manager, right-click on this. So we right-click on this, and then we go down to Order, and then we send that to the back.
We got this right one.
So where's the?
Yeah, yeah, but we don't have to do it.
Got it?
Yeah,
Oh.
we got it.
People got it? Yeah? A nod of agreement or something from everybody, a thumbs up? Is that a thumbs up? Good? Yeah? Okay. And what we're going to do, centre back. True colour, blah, 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 blah. Okay, number 9. So we have poor contrast in the Landsat image. So what we're going to do is, again, so now we've got 2 images on top of each other. The reason Envy loaded these 2 images on top of each other, you can see that it's the same patch of ground, right? It's geographically registered, these images. Yeah. Both of these images have this geographic information. So for every pixel, we have a latitude and longitude, or a UTM coordinate that locates it specifically on the Earth's surface. And that's why Envy just automatically just planted one on top of the other. If they had no geographic information, Envy wouldn't do that, because it wouldn't know how to do it, because it wouldn't know where these pixels were on the surface of the Earth. So in this case, what you have to do is,
Write your own Python. Those astronomy back.
so you'll see, if I click on the ETM1 image, everybody, I get this black box that appears, right? What that's telling me is I've selected the EO1 file, and any image processing I do will happen on the EO1 file, right? So, because I want to change the contrast of the Landsat image, I need to make this box go away by selecting the Landsat image, right? And you'll see in the file manager, this was highlighted as soon as I selected that, right? If I collect this, you'll see that the EO1 thing gets selected, right? And that, okay. So now any image processing I apply is going to happen with the Landsat image. I'm sorry if this is tedious, but quite often people don't select the right file and then you end up hitting buttons and nothing happens, right? Okay, so what we're going to do is change the contrast on this, and we're going to do that with this histogram stretch. So up here you'll see this thing that looks kind of like a histogram, right? And I think I put a shortcut in there as well,
Not
but
that one.
see that icon there? And if you float over it, it literally says histogram stretch.
This one.
Yeah. So click on that and then you get this thing that looks like this. So let's just move it off to here for now. So this is, they didn't do a very good job of annotating this GUI, but the what you see here is a histogram of the DN of all the pixels in the red band, a histogram of the DNs of all the pixels in the green and the blue, right? Where the y-axis is number of pixels and the x-axis is DN, right? So what that's telling me is that the DN range for the Landsat ETM Plus image is 0 to about 250. So does that sound suspiciously like 255? So what's the data depth of Landsat? Right, which is in bits. 8 bits, right, or byte data. Okay. So Landsat distinguishes 256 different intensities or brightnesses, or how, and the way to think about that is, if this pixel on the ground is reflecting slightly fewer photons than this pixel on the ground, can I work out that they're different, right? And the more gray levels I have, the more chance I have of distinguishing that that pixel is reflecting, yeah, this is slightly more photons than this pixel. So these are the histograms, and what this is telling me is in the red channel, most of the pixels in the Landsat image in the visible red part of the spectrum have a DN of around 25, right? This is number of pixels, so if you just, the area under this curve, most of the pixels have a DN of somewhere between like 20 and 40, right? Which is why the contrast is so poor. Okay. Same thing for the green, and then for the blue we've got this over here, right? So to change the contrast, I think, in Photoshop there's probably just a button that says contrast or something like that, right? The way they do it here dates back to when they used to do this vaguely manually. If you roll over the left-hand side, you'll see that on the left-hand side, my cursor just changed to these double-headed arrows, right? So if you click on that and move it to the right, you see that red line? So I'm going to drag it to about here, and then release it. And then I'm going to do the same on the right-hand side, and I'm going to drag it all the way into, I don't know, about here. Right, and magic happened. Okay.
What did he do? Okay, let's look at what this is for Jackie.
Everybody got a similarly crappy result? Okay. So what I've done here is I've said take any DN in the original image which is less than 19 and make it 0. Make it black on the display, right? I've said take any DN in the image which has a DN of greater than 50 or 49, right? And make it 255 or white. And then take all the others and stretch it out between 0 and 255. So in pictures what I've done, you ready? This is the explanation of contrast stretching, right? I've grabbed that point on the tail and that point on the tail, and I've stretched them out from there to there, right? And in that way, instead of displaying all of the pixels in this image with display values of between 19 and 49, I'm now displaying them all between 0 and 255, which gives me a more dynamic range on the display. Okay. Now I've only done this for the red band, right? So I've saturated the red channel, which is why it looks red, right? So all you've got to do is just repeat that for the other channels. So just do the same thing. So down here on green, I do that, and this is not a precise science.
But what does it want? Same thing.
Again, this is, so just do it by eye. This is not high science. And I'll take that to there. And I get something that looks a bit better, right? Because I've adjusted the contrast in each of the 3 display bands, and I could probably.
Get some more stuff. Same number.
But I can just tweak this.
Oh, sorry, I didn't. 55.
And the other thing as well, if you noticed, if you know where you want to stretch it, you can just type numbers in beneath it and just hit enter, and it will do it, right? The people agree that the new image is a much better version of the old image for like interpreting it and drawing lines on it and mapping stuff, right? Yeah. So that's just a contrast enhanced image, right? So the first thing you do when you get an image of Mars or Mercury or the Moon, so there's no wrong as long as it looks okay. Yeah. So there's no right and wrong.
Yeah, then
Yeah. So move that out of the way. There we go. Right. So it's kind of similar. And we could balance these exactly. Right. We could balance these exactly so that they look really, really similar. Whenever you get a satellite image, the first thing you're going to have to do is change the contrast, right? Because usually the measurement range, usually the number of photons or the reflectance only uses a small part of the dynamic range of the instrument. First thing you're going to do is do a contrast stretch. And I think you can see, right, if I was interested in mapping lava flows, so this is Mauna Loa, right? Mauna Loa is kind of over here, Mauna Kea is up here, Kilauea is here, right? Kilauea is this kind of thing, right? So this is Mauna Loa. The eruption last year was over on this flank of the volcano. If I was interested in mapping the lava flows of Mauna Loa, I could probably do it from this image, but I couldn't do it from the other image, right? So first thing you have to do is do a contrast stretch. But this is purely cosmetic, so it doesn't change the DM, right? It's just display. So I can make this whatever I want. And I didn't. Right, that's horrible, but it's right. That's horrible, but it's okay because I can fix it. Right. Right. So you're not damaging the data or anything like that. Just play with this. And the thing with this is there's no magic recipe. It's just until it looks good. Right. Other things you can see on this. So this isn't active anymore, but this is Pu'u'o'o. So that was a vent on Kilauea that was open for a few decades. And that basically all shut down. You remember the big eruption in 2018? What year is it now? 2025. Is it? No, it's
23.
23, right.
Now this year.
So actually that was a long time ago. So you weren't here. Is anybody from Hawaii? Okay, great. So you were here during the Kilauea eruption, the Lalani Estates eruption in 2018, right? So that was all the way down here, right? But this vent had been open for about 30 years, and that just completely closed off in 2018, May 2018, when that eruption began, right? And all of these lava flows that you see here poured out of vents here, and then another lava lake called Kupaianaha, which is just over about here, right? The summit of Kilauea is up here, so that's where the old museum was, right? So this image was acquired in 20. Did I actually put it down in this thing? I don't think I put it down. It might not be in the header, but they were quite at different times, but clearly this was before the summit lava lake had appeared. Anyway, so that's how you contrast stretch an image, right? What are we doing now? Yeah, well, that's that spectral. Okay, right. I've got max. Oh.
Maybe like, oh, maybe here.
Okay, so what we're going to do now is we are going to.
No, I can't scroll.
Layer manager select L1.
I have to go down here in order to do the. Okay, that's not.
Ah, right, okay. So this is in layer manager, it seems. If you click on that,
Okay.
let's close this, right? Let's close the contrast stretch box, because otherwise it gets really cluttered. And then here,
Close this box.
and I think I had it as
I'm
Alt.
afraid If I do this,
Z.
remember last time
Oh.
it kicked everything off.
Okay, that's obviously something on my.
Probably a button.
Were you able to exit the histogram stretch and not have the whole thing close?
Of course he can.
Anytime she opens something and closes it, it just closes the whole program.
Right, yeah, that's a feature, I think, of a Macintosh.
Okay, so we have to open
Let's
first,
open.
open the EN first.
Actually, let's open them.
Oh, for Christ's
that one
No,
first.
I'm
So just
opening
do
the right
open reset.
file, even after I extract everything, and it just won't show.
Which one is the?
So just
So it
do
should
open
automatically
reset.
show like
Do
a-
open reset, that'll be easy.
like an estimation of what it would
Wait,
look like,
where-
and it just
Okay,
won't.
let me get rid of this.
Right, so what you need to do is open those two files
Okay.
again.
Okay, file, open reset.
So this is vaguely chaotic, but I guess that's what you get. Next year I'm going to tell people that
Okay,
they
but
have to
this
use
is
Macintosh.
the right one, so just
Sorry, the other
open
one.
it. Yeah,
Right, so you're good,
So-
you're good.
we're not,
Yeah,
okay,
that's
all right, so
You're
now
good.
let's
File,
open,
open.
You are good. You are
open
good.
file,
No, open,
and
not
it
open
is,
as, there you go.
and
Now
it is the
should be
BSN.
BS.
BSQ, yeah, that one.
Oh, no, that's not the one. It's the DN.
Oh, yeah, this one.
There
Yeah,
you go.
that's it.
Okay, don't hit that button to get rid of it.
Yeah, no. Maybe just click the,
Right.
get them
All
out.
right.
So now, let's do this. So let's go, let's make that full. We will go here, and we will go right click, order, bring to front.
Okay.
Right, and then we'll
Right, into front.
zoom in a little bit.
Okay,
Okay, so what we're going to do now is we're going to produce spectral profiles or spectra from both images and compare them. But the way you have to do this is highlight, you can do this one first, right? Highlight this in the layer manager and then click spectral profile,
this one, right?
right?
And click
And you should get
scroll
something,
away.
you should get a box like that appear.
Spectral profile.
Everybody got it? Hand up if you've got it.
Where's the spectral profile again? Remember? Is one of these guys.
Oh, so your windows don't display, right? Okay, then you'll skip this part.
The spectral profile.
Very spectral.
Right, and then
Do you have your other
to get the spectral profile for the same pixel from the other image, you have to click on this and make that go blue, right?
This one.
And then click on spectral profile again.
And
Right.
blue.
Who has got that?
Well, you want it for the same point.
Can I have a hand in the air for who has got that?
So then click spectral profile.
This one.
You got it, right?
We got it.
Over at the back? You've got it? Okay. So again, because these two images have geographic information, Envy has automatically co-registered them, right? Overlaying one on top of the other. So what we see here is, for whatever pixel I click in, ready? For whatever pixel I click in, on the top it's showing me the DN spectra from the EO1 Hyperion sensor, and beneath it it's showing me the DN spectrum from the Landsat Enhanced Mapper Plus, right? So things that you can recognize in these curves, remember I said Landsat was low spectral resolution. We have like 6 channels between the visible blue and this kind of shortwave infrared. It doesn't give the plot symbols, but that's one. You know, see, this is like a sequence of lines joined up, right? And the inflections are the band centers, right? So if you just follow my finger around, we have band 1, band 2, band 3, band 4, band 5 is about here, and then band 7 is this one out here. On Landsat, we have bands 1, 2, 3, 4, 5, which are between 0.5 microns and 1.5 microns. We then skip a band and go to band 7, which is at 2.2 microns. And then Landsat has a thermal channel, which is band 6, which is out here at 12 microns, right? The reason it's like that is because band 7 was a late addition to the Landsat thematic mapper design. So people realize band 7 is really good for mapping clays and hydrated minerals, right? They already had bands 1, 2, 3, 4, 5, and 6, right? So that was, they already had in the design 1, 2, 3, 4, and 5, and 6 out here in the thermal infrared, right? And then as a later addition, they said, we really want a band here at 2.2 microns that can map clay minerals and hydrated minerals, right? At that point, they had a choice. They said, well, we should really call this band 6, not band 7. But then somebody pointed out, well, we are going to have to change all of the documentation associated with this mission. And that's not a trivial thing, right? So an important thing in spacecraft is interface control, right? So when you start a mission, you don't want confusion about what band 6 and band 7 are, right? You don't want somebody saying, oh yeah, I've got band 6 covered, yeah, and they're really talking about band 7. So when they were doing this, they just decided they would just have a shitty order for the bands. And band 6 would be all the way out here, and there'd be a gap between band 5 and 7. So that's the explanation for why that happens. But that stuff's important. So when you're designing your missions, there's a ton of documentation, right? Because you can't just keep it all up here. So 6 measurements here, these are so closely spaced that we can't distinguish them, right? This is a complete spectrum. And they both look the same, right? So this is a spectrum. Oh, click in the image of the Hyperion image, right? That looks like that, right? It's just less rich because this is lower spectral resolution than this one, right? If we click here, so this is, and let's just zoom in a bit, right? So if you just click on one of these pixels, let's just take that one.
That's right.
Right.
That one.
Okay. So can I convince you that these are also grossly similar to each other, right? Let's just map the patterns. Here, I have high radiance in the visible blue, which goes down to the visible red. Here I have high radiance in the visible blue, that goes, sorry, DN, but it's the number of photons, right? High in the blue that goes down to the red. It then goes up quickly to the near infrared, and this goes up quickly to the near infrared. And then it kind of goes down across the shortwave infrared, and then down again to this kind of band here. Now, this slope is steeper here than this slope, right? And the reason for that is these are in DN space, and the calibrations between radiance and DN are different for this sensor, the ETM Plus, than they are for this sensor. But that goes to show, you remember I said that DN is a crappy number. That doesn't mean anything. And that just shows why it's crappy, right? The DN is a made-up number. We can certainly use it, but a lot is hidden in the calibration, right? The slope of those calibration curves. So this curve is fundamentally like that, but there are some differences. And the difference, the fact that this slope is not as steep as that slope is because of differences in the radiance DN calibration between this instrument and this instrument. So again, we can make pictures, and if anybody's done clustering or image segmentation or classification where you're just trying to say to a computer, find me pixels which are similar to each other, right? That works perfectly well in DN space, right? But if you want to actually do some of this spectral fingerprinting, you can't use DN space. Right? You have to go to radiance and then to reflectance in order to do that stuff. So there aren't many others. Let's just look down here. So this is a lava flow. And also remember, in the Landsat image, we have some clouds which we don't have in the CA01 image, right? So, you know, be careful about that. But yeah, so that's what the low spectral resolution, high spectral resolution shapes are kind of similar because as I've shown in class, dn is proportional to radians, right? But the constant of proportionality can vary by sensor and by band, right? So you get different shapes. Who is having fun? Vaguely interesting, right? Okay, so where am I? Where am I? Where am I? Oh, we're on 10, right? We're on part 10.
Oh, 10, great.
Okay, right, so here we go. So now we're going to navigate to a specific pixel within this image. So this is point 11. So, so there's this thing here which is go to. So you see this box up at the top? It says go to. So that allows you to type in a coordinate and go to a particular pixel within the image, right? So what I'd like you to do is type the numbers in the handout in point 11. So what am I doing? 297,185, comma 215,9140. And then just hit enter.
Wait.
I guess count.
Oh, I see it. It's in this way. That's this way. Okay, sorry about that. Yeah, no, it took a
Okay,
while.
so you have exactly one.
Okay.
And unfortunately for you, so that worked, but you can't see the spectrum.
Are we supposed to see two? Oh, this is.
That's good.
Remember
That
we
is,
closed it out.
that is
after we
good.
changed the times.
That's, so you're just going to type in those coordinates, right? Or something.
Yeah.
That looks good. Okay, don't do anything else.
Don't touch it.
So, so again, we've just gone to a different pixel and we're looking at the same thing again. Again, we've got down, up, and then we've got down, but this is kind of a bit weird. So we go there, and then, so this pixel contains vegetation. So now we're going to compare this with the reflectance spectrum of actual vegetation, right? So if we go to this thing, so point 11b, in Spectral Library Viewer, Spectral Library Viewer, which must be on the toolbox, I guess. Spectral.
We want the library. No. So, where is this cursor? Those are kind of like manipulations.
Oh, okay. So I don't think I put it in, but Spectral Library Viewer is here under Display. Right, so under Display, you go to Spectral Library Viewer. Yep.
It's just right there.
You good? Yep.
Yeah.
Right, so I get this thing. Has everybody got something that looks like this, an empty window? Right. So if you just click on one of these plus signs on the left-hand side. Click on USGS 6. Right? And you get a load of extra things that just appeared. Right? And then I'm just going to click on this one here, which is Minerals Beckman. It's got 488 in it. And you see all these names. You can look at the screen as well. So in the Spectral Library Viewer, I just clicked on USGS 6, then I went down to Minerals Beckman, this one, and I clicked on it, and then I've got all of this stuff going on in here, right?
USGS 6.
Are you clicking on a specific image?
No, no, this is separate. This is not, at the moment it doesn't matter which image you're in, so you're just looking at the library viewer, right?
There's also coding.
Okay, that's okay, so they're further up, right? Coatings. And then if you scroll down to Minerals Beckman 3375.sli, you can have it. Okay, it doesn't matter, maybe it's a different library.
Oh, there's a veg library and a USGS.
So open any, right? But then look at my screen, right?
Okay.
So what we've got here albite is a plagioclase mineral, right? Actinolite is a mineral that you find often in rocks on the ocean floor, which have been covered in water for 100 million years. Almandine is a polymorph of garnet. Alunite. Anhydrite is that mineral I showed you the other day. It's like gypsum without the water. So what we've got here, anorthite is a plagioclase. What we've got here is loads and loads of different minerals, right? These are library spectra. So if I just click on one, I'll click on that one. Okay. So the people, what do you think that is?
That's the same thing we're looking at with the spectral profile.
Right,
Yes.
except, right? So that is a spectrum, right? We've got a spectrum in here and a spectrum here. This is DN against wavelength for an unknown target. I mean, I told you it's vegetation, but it's
Yeah.
DN against wavelength. This is reflectance, so 0 to 1, right? Against wavelength for a known target, right? This was a lump of anorthite crystal that they ground up into a powder, and they did what we did the other day in class. They ground it up into a powder, they shone a known source of light onto it, and they measured a reflectance spectrum, right? And then they recorded it and they stuck it in this library. And then they did it for all of these other minerals. So these should start looking familiar, right? Remember I said reflectance remote sensing was squiggle hell, right? These are all reflectance spectra measured in the lab by taking known mineral samples, right? So a geologist comes in and says, here's a sample. Grind it into a powder, put it on the table, shine a known source of light onto it, measure the reflectance, record that reflectance, and then dump it in this, which is a spectral library, right? So if we just go back to another one, I will choose, what's this one? I don't even know what this one is. So loads more minerals, but here's a dry grass. So that's the spectral signature of dry grass. Hematite, this is the thing that makes rocks look red when you rust them. Right, so in that case here, look, we've got high reflectance in the red, lower reflectance in the green and blue, which is why hematite looks red. Okay. So envy, remember when I said what we do in Mars might be that we go to a pixel and we extract a spectrum and we convert it to a reflectance spectrum, which I'll show you how to do in a minute. And then we say, well, I don't know what's on the surface there, but I can use that run length encoding algorithm that I showed you to go and find the best match in a spectral library, right? That's the spectral library. So you just match it against what's in the library, and then the best fit, which will be some kind of minimization, some kind of, when the chi-squared hits the minima, that's the best fit, or something like that, right? In the run length encoding algorithm I showed you, it's where you get the highest percentage match, right? Then you say, well, the spectrum I'm measuring on the surface of Mars is really, really like, and it wouldn't, well, really like hematite. So I am N% confident that what's on that part of the Martian surface is hematite, because it looks really like hematite. Okay. And we're not going to do it here, but there are a bunch of algorithms in Envy that just allow you to do that. And obviously, you know, Envy's, it's image processing software, so it's designed to help you get the right result. However, in the same way, you know, if you have an idiot driving a car, you're likely to have an accident, right? So you have to know how to use it, and you have to keep your wits about you. It's not magic. It doesn't do it for you. But the tools are in here where you could do that. You could get an image of Mars at different wavelengths, and you could do this matching kind of almost autonomously to produce a map of hematite on the surface of Mars. And you remember if I showed you a few weeks ago, we had some maps, right, which mapped hematite on the surface of Mars. They were produced by doing this, taking a pixel off Mars, take the spectrum, match it to the library, work out which pixels contain hematite and which pixels don't contain hematite. So what we're going to do in this part of the lab is, okay, so let's close this again and open it, because I do not know how to clear that. Right. So let's just close it, and then we'll go display, spectral library viewer, right, and we'll just open it up again so that we clear it.
Okay.
And then I'll move that over here,
So it's clear.
and I'll move that over
You're
here.
good.
And then, this is one then, maybe this is different. So if I go to, do you have this one, veg lib at the bottom?
Yes.
Yeah.
Okay, right, so click on that. And then if we go to Veg 2, right? Click on that.
I'm okay, but it's not.
So what do people think veg is?
Vegetation.
Right, okay. So it's not just geologists that do remote sensing work, right? There are people that care about plants. And remember, we eat plants, or the things we eat plants. So it's good to care about plants. And they also want to map plants on the surface of the earth. And they have done the same thing. They've just gone out.
This is a coating.
Yeah, so if you're in coatings, we're in the wrong one.
Yeah.
Well, now we have two veg, but it's not the
I
same
think the
one as
second
yours.
veg one is
Veg
that.
2. Yeah, just go to the second one.
Okay.
Yeah,
Okay.
go to the second.
Oh.
Click on that thing next to it, the plus, and that will expand the menu.
It looks like the
And then
same.
scroll down a little bit.
Oh,
Okay,
good.
now stop.
Ah,
So look at all those words that are there, and maybe some of them are more familiar to you than mineral names, but you've got different types of leaves and trees and stuff like that, right? So the other day when we did that reflectance spectroscopy, I went outside and grabbed 3 leaves, right? And I don't know what that plant is outside, right? Does anybody know what the plant is outside? Oh, now they do. So I brought in 3 leaves and we put them down on the table and we shone light on them and we measured the reflected light that came back. That's all that you're seeing there. Again, scientists went in and said, I care about mapping bay laurel, whatever that is, right? And they brought a leaf in and somebody made the measurement like we did the other day. They measured the spectrum and they put it in a library, right? So don't do it now, but if you go through these spectral libraries, you'll find they've done this for everything. So they've done it for asphalt, roof shingles, different types of water, different types of soil, all types of rock. Right. Anything that we might want to map, they've done what we did in class the other day. So now we are going to go down to live oak. So live oak is just here, right? So if you click on that, we get this, right? That's the spectral signature of live oak. Okay. And remember, this is reflectance. So this is between 0 and about 1. It auto scales, but this is 0 and 1 wavelength, right?
this is in my
What are we doing now?
micron, so this is times 1,000, so it's 500.
Okay, so I've told you, right, here on the right hand side, we're looking at the DN spectrum in Hyperion, as measured by Hyperion and Landsat, for healthy green vegetation, right, and I promise you that's true. On the left, we have the reflectance spectrum of vegetation, right? How are these curves similar and different?
That one goes up to 0.6 while the other ones are only going up to.
This is 1,000.
Oh, but remember, these are DN,
Okay.
this is reflectance.
The beginning thing.
Yeah.
This is the wavelength.
So let's just see how they're shaped, right? Because remember, spectral signatures are all about shape. So the troughs are where we're having Z number dependent absorptions, which tell us about chemistry, okay? And then the peaks are wavelengths at which we're having less absorption, Beer's law and all that sort of stuff, which means we have a reflectance peak. So healthy green vegetation looks green because we have absorption of visible blue photons,
1,000 is right.
absorption of visible red photons to power photosynthesis. Chloroplasts don't absorb visible green light as well, which is why we have a little reflectance hump in the visible green, which is why when we look at a healthy green plant, it looks green to our eyes, right? And if you remember the other day, I said an evolutionary adaptation to stop vegetation overheating, it reflects a lot of light in the infrared, right? So the spectral signature of vegetation, if you take a leaf and you measure reflectance, is trough, peak, trough, big rise up the red edge to this plateau. And then you'll see it drops from here to here, right? And we have like a deep absorption feature and a deep absorption feature. So this was measured in the lab. This was measured from 700 kilometers away in space. So how are they different and similar? Well, this kind of feature, this absorption feature and this absorption feature kind of appear, right? They're different shapes, but they're in it. We have this absorption feature in the visible red, which is in both, right? For the vegetation in the lab, it goes down, up, down, from red to green to blue. Here in the space-based measurement, it goes up, and it doesn't go down, it goes up, right? But we have this large increase from the visible red to the near infrared, and then this change. So this part of the curve is kind of the same, right? Different but similar characteristics. But a big difference is this thing here, right? And if we look in the Landsat data, we see something similar. It goes down, up, and then it kind of goes down like that. But here, instead of going down in the visible blue, It goes up in the visible blue, right? So again, this is why if you're just saying that pixel's different to that pixel and you want to do some classification or segmentation, you can work in DN space. But this is the spectral this is the radiance DN proportional to radiance measured from vegetation in space, but this is what vegetation looks like in the lab, right? So this is another reason why if we want to do this fingerprinting, we can't just use the DN data. Right? The reason we have this, the shapes are different, as I said, to a certain extent. This is DN, this is reflectance, right? This spectrometer, I put it in the handout, certain wavelengths are calibrated with one calibration factor and certain wavelengths are calibrated with a different calibration factor, right? So slopes, the relationship between radiance and DN is different in this part of the spectrum than it is in this part of the spectrum, right? And that's just a calibration thing. I'm going to explain to you briefly why it doesn't go down, up, down, right? The reason for that is, so I've said that we're measuring photons, right? And this is reflectance remote sensing, so we're looking at reflected sunlight photon. There are many different types of photon, right? There aren't that many different types, but there are different ones, some that I care about and some that I don't. So if we just look at this, I've said that we're doing reflectance remote sensing, and we're taking photons from the sun, which hit the target, and then some get absorbed at certain wavelengths and others don't, and we get reflected photons back. They come back and they get to the satellite and we measure them, right? So obviously I care about those photons, right? When you are in shadow, if you go out of this building and the sun is on one side of the building but you're on the other side of the building, you can still see, right? I mean, it isn't dark. Right? On the moon it's dark, but on the Earth it's not dark. Why is it not dark on the Earth when you can't see the sun, but you can still see stuff around?
It's reflecting off of other things.
Yeah, not bad. Yeah.
Well, it's being scattered from
Right.
the atmosphere.
Right, so our sky, the constituents of our atmosphere are scattering sunlight. The sun's coming in and it's not seeing me, but it's hitting the sky all over the place. And that sky is backscattering it into the shadows, right? And that's why we can see in shadows on the Earth. That's why there is no light in shadows on the moon, right? Because there's no atmosphere to scatter the light. So let's just look at these photons. So these are photons that come from the sun, get scattered from the sky, hit the target, and then come back to the spacecraft, right? The spacecraft, the instrument doesn't know the difference, right? It just the telescope just gobbles up these photons and splits them and then records them and then converts them into a DN, right? Class D photons are these photons where it hits a target beside our pixel, bounces, gets down scattered from the sky, and then gets changed by the target and then gets bounced up to the spacecraft. The instrument just records those photons and it just mixes them all up, right? And then, you know, some other types of photons, so these hit a completely different type of material and get bounced into the field of view. These photons never touch the target at all, right? They hit the sky, and then the sky just backscatters them back to the spacecraft, and the telescope gobbles them up and it records them. Right? So we're not going to go into too much detail, but I'm just going to explain that up, down, up. Instead of going up, down to from the red, which way am I doing it? From the red to the green to the blue. In our satellite data, it goes low in the red, up to the green, then up to the blue, right? And the reason it does that is because our atmosphere scatters blue light very effectively, right? So in addition to photons from the ground, the satellite is also measured a load of blue photons which never touch the ground. They just get backscattered from Earth's atmosphere, right? And that's why in all of these images we have this kind of thing going on, right? Instead of going down, up, down like real vegetation, I'm seeing reflectance from the ground, which is why these curves look kind of similar in places. But superimposed on it in the satellite measurement is I've got this reflected blue light, which is just backscattered atmospheric radiation, right? And here's just an image of what that looks like. This was acquired by an airborne sensor flown over Kilauea volcano. This is the visible blue. This is like shortwave blue. You can't really see what's on the ground, right? I mean, I can see this plume and I can see this cloud, but you can't make much out. This is the same point on the ground, acquired at exactly the same time, but in the infrared, right? And you can see I can map all these lava flows and I get a nice crisp image, okay? These images look different because at this wavelength I'm measuring, for each pixel I'm measuring photons reflected from the ground, but on top of that I've got a load of photons which never touch the ground, they just got backscattered by the atmosphere. The particles in Earth's atmosphere aren't large enough to scatter infrared light, right? Unless you have a really cruddy atmosphere. So you know when you see like these gorgeous red skies and orange skies, that's because you've got, you know, you're in LA and the atmosphere is poisoned. Or after a large volcanic eruption, you can get these red skies, so the screen, every bunch of screen painting, right? So the beautiful red sunsets. Volcanoes inject aerosols which are larger than those typically found in Earth's atmosphere. And they are large enough to scatter not just blue light, but red light, right? So typically those particles aren't large enough to scatter IR light. So here we're just measuring mainly ground reflectance. Here we're measuring the sum of ground reflectance and atmospheric backscatter, right? And that's why instead of going down, we get down, up, right? So, as I said before, if you don't want to correct for the effects of the atmosphere, you should not do remote sensing on the Earth, and you should not do remote sensing on Mars, and you should not do remote sensing on Venus, right? So people that look at the moon don't have to worry about this because there is no atmosphere on the moon, same for Mercury, same for Pluto, all that sort of stuff, right? I point this out because this is an important part of this science traceability process, right? If I say, well, I need this satellite sensor and I need it really precise and I'm going to measure, you know, something really complicated about the surface of the Earth, it's an engineer is certainly within their rights to say, well, can you justify that you need that level of precision? Because I hear your ability to correct for the atmosphere is kind of crap, right? So it's a bit like that thing. If you have if you're trying to solve a problem and you have a bunch of terms, the term with the largest error might very well dominate the uncertainty in the thing you're trying to calculate on the left-hand side, right? So there's no point if you have 10 terms and one of them is raised to the power of 10 and you have no idea what its number is, there's no point making all the others really precise, right? It's a waste of time because all your errors coming from a completely unknown term which is raised to the power of 10. So in science traceability, these are valid questions, right? And in this case, when you're remote sensing the Earth, you have to justify that you can do a decent job of correcting for the atmospheric effect. People still okay, right? So what were we doing now? We're going on a bit here. What time do we finish? Is it 1? Blah, blah, blah. So we are going to skip a few things. So people good. So what I've shown you so far is, and you should finish this off on your own, right? We've got through most of the way. Differences between you've learned a bit about ENVI, and this you can now get into it and mess around with these things. DN is okay if you're just like looking at differences, but if you want to go to actual spectral fingerprinting, you can't use DN for these kind of reasons, right? The other thing you have to do is correct for the effect of the atmosphere if you're on a planet with an atmosphere, as I've just shown you. And I'll just give you an example of that quickly. So this is something I did very quickly, so this isn't very precise. One way that you correct for the atmosphere is you build a model of the atmosphere. I think I mentioned this before. So we use a model called MODTRAN, which is a radiative transfer code, which was developed by the Air Force years ago. If you think about it, if you're trying to shoot down a missile is warm, right, because it has an exhaust. If I know what is combusting, I know the temperature of the exhaust, right? I can work that out because that's kind of chemistry. And because it has a temperature, it radiates photons, right? It radiates a spectrum of light. The further I am away from it, the more of that light will be absorbed by the atmosphere between me and the missile, right? And that's an unknown if I'm trying to work out how far away the missile is, right? So what I can do is say, well, I know that missile should be is at this temperature, therefore it should be radiating this number of photons at this wavelength. But I know that I'm measuring fewer photons because some of them are being absorbed by the atmosphere. So what the Air Force Research Lab did was basically get a bunch of really clever people to write some code that says, well, let's predict how many photons I lose in the game between the missile and me, so that I know I can say, well, this is a nonsense number, I'm measuring 50 photons, but I really know it should be 100 photons. If I model how many photons are absorbed between me and the missile, what's the distance? Right? And if I add those photons back, then I can work out the distance between me and the missile, and I can or cannot shoot it down. Right? So this radiate transfer code was developed by the Air Force, but we use it for remote sensing. And what we do is we take Earth's atmosphere and we slice it into slices, horizontal slices, and we fill each layer with the gases that are in Earth's atmosphere. Right? We put water vapor in, we put carbon dioxide in, we put all that good stuff in, we put some aerosols in close to the Earth's surface. And then we pick the temperature of the Earth's surface, which is appropriate for the geography and the time of day. And we use Planck's law, which I've shown you, to say what's the spectral radiance that surface should radiate. And then using the other Planck law that I gave you, we can convert that into a photon flux at each wavelength. So how many photons are leaving the Earth's surface? And then we just allow them to go up from layer to layer. And at each point we calculate how many did I lose? 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 Until you get an estimate of how many photons survived passage through the Earth's atmosphere. Right? And in that way you can invert that to work out what the atmospheric loss or addition term is to the signal that you measure. So in the last spectrum that I showed you, we had that addition term, right? Right, we had this blue light that was superimposed. So I can work that out using Modtran, and I can subtract it from the signal I measure of the spacecraft and correct for the effects of the atmosphere. So here's just a picture. So this is from the data you've looked at. Here's the spectrum measured, right, for vegetation. So you see, instead of going down, up, down, I've got down, up, up, and I've got this atmospheric bluing effect. So what I did was construct a fake atmosphere. I put the sun in the right part of the sky at the right time of year. And then I shone sunlight down on the ground. And then I predicted how much should arrive in space after it hit vegetation. And that's this black curve here. So that black curve looks kind of similar to this red curve, right? Do you agree? There are some differences. I mean, I didn't spend a whole lot of time on this. I did it pretty quickly. But we have this. It goes up. We have this type of feature. We have a bump. 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 Right? And then the other curves are the different components of the signal. So direct ground reflectance is this one here, and that looks like the vegetation curve, right? I've got down, up, down, up, down. Single scattered and multiple scattered, those are these skylight terms, and you'll see they're high. This magenta and the orange curve are high in the visible blue, and then they go down because, as I said, there's nothing in Earth's atmosphere which is large enough to scatter light at these wavelengths. So for planetary science, you don't do that a lot. I just wanted to show that. That's the next step. So you take your DN image, and then if you're on the moon, you just have to convert to radiance, and then do that reflectance thing that we spoke about the other day. And then you can start matching spectral signatures with libraries. On a planet with an atmosphere, you've got to do this kind of thing, right? To go from the black curve to this blue curve, right? And once you're at the blue curve, then you can start doing the library matching. So the only thing I'm going to show you before we go is I've done all this for you. So this is not what, I mean, I can do it, so it's not that complicated, but this is not straightforward and anybody doesn't do it for you. But I produced a version of the DN image that you've got that has been calibrated to radiance and then corrected for the effects of the atmosphere. So if we quickly just open that, so if we go back to our here, and let's close that, close that, close that. Let's right click here and close all this stuff. And we'll close this.
Yeah, it works.
Remove. Close all those things.
So the map stop.
And then if we go here,
Is it open like follow?
Earth observing 1, Big Island, bottom of the atmosphere reflectance. Right? That top one there. So this is in the handout. Okay. So this is exactly the same image that we've been looking at before, right? Except I've taken our DN image, I've converted it to radiance, and that's in here, right? Spectral radiance. And then I've done this atmospheric effect, correction and I converted it from radiance to reflectance. Right. And if you remember in lab yesterday, we said to convert to reflectance yesterday, I said we're going to shine light on of a known composition and intensity onto a target, and then we're going to measure the amount of light that came off. And we can convert, if you look, one of the equations I showed, it was reflectance is the amount of light that goes out divided by the amount of light that came in. Right? And yesterday, the way we worked out the amount of light that came out of the lamp was we shone it on a perfect reflector and recorded that number, and then just divided one by the other. Right? There are no white things in here that I can use as reference targets. Right? So to compute how much light hit the surface in this example, I have to do kind of that thing that I showed you. I have to take the sun, and then I have to scale it to the Earth's sun distance. And then I do this atmospheric effect to work out how much sunlight made it through the Earth's atmosphere, and then I use that number. And once I've computed that number, I can then relate that to the signal I receive from every pixel, divide one by the other, and that converts radiance to reflectance, which is atmospherically corrected. So if we just look quickly at a couple here. So does that look more like the library spectrum of vegetation that we were looking at? Right? So this is a green field, this is a true color image, this is a green field. Right? That was pretty good. So what's happened? If you remember, in my original DN image, we went down, up, up. There was a load of nonsense in here. It was kind of flat, and then it got weirdly shallow. It's dropped off real steep, and then got flat here. By converting from DN to radiance and correcting for the atmosphere, I've now got something which looks really like a library spectrum of vegetation. And I could feed that into one of these run length encoding algorithms and find pixels in the image which are vegetation. So the ocean doesn't change that much, but you'll see here, these are percent reflectance. So if we look at vegetation, vegetation is kind of bright, right? It's 50% reflective in the infrared. Right, this is reflectance times 100. So it's 50%. If we look at the ocean, it's 4% maximum, right? And that's why ocean's kind of dark. If we look in here, anybody guess what that is? So it's red, right? And this is a simulate true color composite. So whatever is on the ground must be kind of red. Probably not that red, right? Remember, this is an enhanced image, so we've changed the contrast and stuff like that. I'm not sure if I put it in there. Oh, I did. It's that. That pixel is this. So it's red dirt, right? Have you seen those red dirt shirts that people sell? So that pixel there is right there. And this is its signature, which is basically the signature of iron oxide. And it's red because we have a peak in the visible red, an absorption in the visible green, and absorption in the visible blue. And that maps onto basically what happens when you take minerals like these and you rust them to produce minerals like these, which have high in the visible red, low in the visible blue, and the green, which is just like what we have here in this part of the spectrum. Okay, so sorry we ran out of time a little bit there, but things to take from this. First of all, you can play around with Envy and you've got the images, right? You know a little bit how to use Envy. DN is fine if you just want to do clustering and segmentation, but if you want to do spectral matching, you've got to do the steps in here, which you can do at your own leisure, which is to go from DN to radiance, right? But what that gets you, when you apply this calibration equation here, right, this thing here, and I showed you the equation, when you apply that to your DN to convert DN to radiance, what you get is something called at-satellite radiance, or top of the atmosphere radiance. All you've done is a unit conversion, you still haven't solved for the effect of the atmosphere. The next thing to do to convert radiance into surface leaving reflectance is to correct the effects of the atmosphere. Right. If you're on Mars, Mercury, or the Moon, you don't have to bother doing that. That's a lot. So I think I'll see you in a few weeks or something. And then we're going to do this performance modeling stuff. And for those who couldn't get Envy working, talk to Peter and he'll arrange a time when you can sit down with Eric and try and get it working.
You wanna try to do it on the same day?
Before I do that,
I know, I'm having the same
Are we keeping the
problem.
handouts?
Oh, sure, yeah, if you like.
before I do that, I'm gonna try to install Envy on my home PC and then follow this and see if I can just do it on that.
Mhm.
If I can't get it there, then I'll come in and try to organize it.
Okay. I'm having the same problem, yeah.
It's not downloading, the latest version of Fire.
Mm,
Like, I don't really get it on this one, like, the image just won't load, like, I'll select the right file, and
Mine just can't find the file
Oh.
at all.
Okay, yeah, so as I said, sit down with Eric. I mean,
Okay.
to find a file, you want a Macintosh?
Yeah.
Search for it. Have
I
you searched for
was,
it?
so I was able to search
Oh,
for
did you
it,
unzip
it would
it
find it,
first?
when I go to
Yeah, you
unzip
can,
it,
yeah.
it says it can't find it, I'll have it open next to
Right.
me. I'll even like search through all my documents, it'll show up, but when I go to unzip it, it's like it's not there.
So
If
We-
we
We
eventually get it.
tried, yeah.
I'll try. I'm gonna try downloading it
Yeah.
again, and maybe you don't have enough disk space or something.
Well, that'll be a problem if you
It's
try to
so
unzip it and you
No,
don't have enough
it
space.
did, the inflate.
But if you get the files out of the archive, then you
Yeah.
should be able